Hello, and welcome to Part 3 of the module on operating system support for programming concurrent and network software. In the previous parts of this module, we presented an overview first of various network programming mechanisms, the sockets API and the select function that's used for synchronous event demultiplexing. In the previous part of this module, we talked about various operating system mechanisms that support multiprocessing and multi-threading. In this part of the module, we're going to continue with the discussion of concurrency, except now we're going to focus on synchronization and scheduling and the various operations that are provided by operating systems to be able to allow synchronization between threads and processes. There's just one tiny short code example in this part of the module, and as before, we'll cover more programming a lot later. So let's start by talking about what synchronization mechanisms are. Synchronization mechanisms are used to ensure that threads, or processes where threads are running, are able to coordinate and order their operations correctly. There's a couple of different reasons to use them. One is to be able to protect shared objects and resources so that multiple threads don't simultaneously update them and cause corruption. This is what's called race conditions. Another reason to use synchronization mechanisms is to be able to schedule the order in which things happen to go. We'll see that there's a couple of examples we'll look at in just a minute where you want to make sure that certain threads run in certain orders in order to be able to carry out the operations that they are chartered to perform. The first set of synchronization mechanisms we're going to talk about is the simplest and by far the most common in many traditional concurrent applications. And these are called mutexes, or mutual exclusion variables, objects, operations, and so on. What a mutex does is it allows application threads to serialize execution by defining a critical section where only one thread at a time can be running. A good metaphor for this would be the kinds of restroom protocols you find on an airplane, where you've got a critical section, the restroom, where one person at a time is supposed to be, and there's a locking mechanism, and when you go up there and you see it says vacant, you can go in, and when you shut the door, the sign goes to occupied, and as long as it's occupied, people who would like to use the restroom have to queue up outside and wait for their turn. And when the person in the restroom is done, they come out, the lock goes back from occupied to vacant, and another person can go in. Note also in that particular example that this is what's called a fully bracketed use. The person, the thread that acquires the lock, is also the one responsible for releasing it. There's a couple of different kinds of mutexes. One kind, which is very simple and often has direct hardware support, is called a non-recursive mutex. And what happens here is that once you as a thread acquire and own a mutex, then you have to release that mutex before you can try to reacquire it. Otherwise, the attempt to reacquire it will fail, or deadlock, or bad things will happen. Likewise, of course, the thread that owns the lock has to release it before others can get it, including itself. The other kind of mutex is called a recursive mutex. And in this model, a thread that owns the lock is able to reacquire it. And all that really happens under the scenes is that a counter is bumped up that keeps track of the nesting level. And at the end, when a thread is done, it can go ahead and call release on the mutex, and it needs to make sure it releases it the same number of times that it acquired it. And when it finally has that lock count drop to 0, then other threads can come along and get the recursive lock as well. As you might imagine, a recursive lock is a little bit more expensive than a non-recursive lock, and we'll take a look later with our one code example in this part of the module to illustrate why it's more expensive. The next type of mechanism we're going to look at is something called readers-writer locks. And these types of synchronization mechanisms allow multiple threads, the readers, to access a shared resource at the same time. You can simultaneously read the information that's protected by the readers-writer lock. But only one thread at a time is allowed to be a writer. And when a writer gets the write lock, then the other readers are kept at bay until it's done. And of course, other writers are also kept at bay until it's done as well. Readers-writer locks are particularly useful for applications that read data many more times than they write it, and this especially works out well if you're running on a multi-core or multi-processor environment where there really is the true ability to carry out multiple computations in parallel. The next type of synchronization mechanism we'll talk about is something called a semaphore. Semaphores have been around for many, many, many decades. And essentially what they are non-negative integers that can be incremented and decremented atomically. And a thread or a process that tries to decrement a semaphore that's 0 will block until the value of the semaphore gets greater than 0. Likewise, when it's able to get access to the semaphore, then it can do its work, and when it's done, it goes ahead and releases it, letting any other block threads know that it's available. It increments the count by 1. Semaphores are often implemented by things called sleep locks, which trigger a context switch, and that makes them a little bit more expensive to use than a mutex. Another thing that's important to remember about semaphores is, unlike mutexes and reader-writer locks that are bracketed, in other words, the thread that acquires them must be the thread to release them, with a semaphore, the thread that acquires the lock doesn't have to be the one to release it. And that allows more flexible scheduling of operations between threads, because you can have one thread that acquires a lock and then another thread that releases it later, the semaphore later, when conditions occur that allow that to happen. Let me give you an example of semaphores that I learned when I was a graduate student at the University of California, Irvine, many years ago. As you can imagine, Irvine, California is very close to the beach. And we used to go out on the weekends and play beach volleyball. There's lots of really great beach volleyball lots down at Corona del Mar and other beaches in the area. And when you go down to those beaches, there's typically, maybe a half dozen or so volleyball nets, but there's always a lot more teams that want to play volleyball than there are nets and balls. And so the way that we would manage the access to the nets was by using a semaphore model. We would have a basket full of beach volleyballs, maybe one for every available net. And the protocol was you would send a representative from each team that wanted to play over to the basket. If there was a ball in the basket, that representative could take the basket and the teams could play volleyball. When the basket got empty, the next group that wanted to play volleyball would have to go and wait for someone to finish their game and return it back into the basket of beach volleyballs. So just a simple example that illustrates the use of semaphores and counting semaphores. Another mechanism we're going to talk about here is a little different from the ones we've just discussed. Things like mutexes, readers-writers locks, and semaphores are often used to keep other things at bay while you do your work in a critical section, like the beach volleyball example with the nets. This next mechanism we're going to talk about, condition variables, is somewhat different than that. It's used to keep yourself at bay until conditions change so you can make forward progress. Condition variables are also used not necessarily so much as ways of synchronizing, but more ways of coordinating and scheduling threads to run in particular orders. Typically what you do with a condition variable is you wait on some condition, which could actually be fairly complicated, until that condition becomes something that allows you to make forward progress. And we're going to see in a minute or later in the course that we can use this particular set of mechanisms, these condition variables, as the building blocks for other more powerful patterns, things like active object, things like monitor object. Let me give you a couple of examples of how condition variables can be used. One classic way that they're often used is to implement synchronized request queues, where you can have threads enqueue something and then another thread dequeue it from the queue. And you would typically use a pair of condition variables called not empty and not full in order to be able to allow those threads to insert and remove messages from the queue in a way that's thread safe and efficient. We'll talk more about this in more detail later. Another more lighthearted example is one that's illustrated here with the pictures on the slides. So imagine that you decide that you want to take a second or third job to make some extra money, and you decide you're going to become a pizza delivery person. Pizza seems to be a growth industry in a lot of places. People like to eat pizza. They eat pizza when times are good. They eat pizza when times are bad, and so on. And so you can imagine that perhaps you and some of your friends go to the local pizza restaurant or pizza delivery restaurant, and you have to follow the following protocol. What you'll do is there might be some limited number of pizza delivery trucks or cars, and of course there'll be some number of pizzas to be delivered. And in order for you to be able to go and make a delivery, you've got to have two pieces of information. You've got to have the pizza, and you've got to have the keys to the pizza delivery vehicle. And if you only get the pizza or you only get the keys, you can't make your delivery. So the way this would work is you and your friends would sit around the waiting room sleeping, since this is a second job. And when the cook is done with the pizza, he rings a bell, and that wakes everybody up. And then they try to get the pizza, and they try to get the keys. And you have to make sure you do things in the right order, or you'll get deadlock. And so what you can do in this case is if you get a pizza and you get the keys, then you can go ahead and deliver things. Your complex expression has been satisfied. If you only get one of those resources because someone else has got them, then you have to release the resource and go back to sleep until you get reawakened again the next time the bell rings. So that's just a simple example of how you can use condition variables to wait for things to happen and to be able to schedule and coordinate the activity with multiple executing agents, threads, pizza delivery people, and so on, in order to carry out those tasks in a coordinated order. So to summarize this particular section, synchronization mechanism performance often depends on a number of factors. The way that they're implemented in the operating system, the type of hardware that's used, the use cases under which they're going to be applied, and so on. There's a couple of common ways of implementing these things. One is by using so-called spin locks, which will do a busy wait without sleeping until the resource, the lock, is acquired. This is sometimes used with low-level hardware test and set operations for mutexes. It's very lightweight, but you could busy wait for a long time. The other extreme is something called sleep locks, where the system actually puts you to sleep until you can make progress again. That obviously doesn't incur the overhead of busy waiting, but on the other hand, when you do a sleep lock, there's a context switch and a fair amount of overhead to put something to sleep and wake it up later and so on. And so some systems actually provide hybrid or adaptive locks that will try spinning for a short time, and if they can't acquire the resource, then they may go ahead and sleep. So different implementations do things in different ways. Some other issues to keep in mind as far as performance and capability are the following, if you want to have the different mechanisms duke it out to see which one to choose. Condition variables and semaphores are generally more expensive in terms of overhead than mutexes and reader-writer locks. And that's because they often will do sleep locks as opposed to spin locks. On the other hand, they're also a lot more expressive. There are things you can do with a condition variable you can't easily do with a mutex. In fact, it's also worth pointing out that condition variables typically use mutexes to do their processing, as we'll see in just a second. Mutexes and reader-writer locks, when you compare those two, mutexes are generally lighter weight. There's less going on. But on the other hand, if you have multi-core or multi-processors and an application that can have things run in parallel, and you have a lot more read operations than write operations, then readers-writer lock may be the choice for you. Non-recursive mutexes are typically more expensive than recursive. Non-recursive mutexes are typically less expensive, lower overhead than recursive mutexes. But on the other hand, non-recursive mutexes are also more error-prone. If you make a mistake and have a recursive call, or you have mutual interdependent calls in a program, you can end up with self-deadlock or other kinds of scheduling hazards in that model. So the key thing to remember here is that not all operating systems support all of these different synchronization mechanisms. So you may either have to limit yourself to the ones that are most commonly available. A mutex is pretty much available everywhere. Or you may end up doing some emulation in order to build on the mechanisms you do have in order to emulate the behavior of the other ones if you want to get that portability. Here's just a simple piece of code that illustrates a part of a recursive thread mutex. This is based on some of the things we've done in ACE. As you can see in here, the acquire method comes in. It uses the C++ resource acquisition is initialization idiom If you take a look at this in Wikipedia, you'll find how that works. To be able to grab a mutex to ensure you have only one thread at a time inside of this critical section. And then it goes through with that lock held and it checks to see the nesting level. If you're trying to acquire a lock that has a nesting level of 0, you can become the owner. Likewise, if you already own the mutex and you're trying to acquire it, you just increment the count by 1. If you don't own the lock or someone else owns it, then you have to wait while the nesting level is greater than 0. And here you can see where we use a condition variable in order to do that wait operation. And the way this works is when you call wait, it releases the lock and goes to sleep. And then when someone later releases the lock, we don't show this code here, but when the lock is released, that would cause the nesting level to have been incremented by 1. And then you could go ahead with the lock held, check that condition, and see if you can make progress. So this illustrates a couple of things. First, it shows how we can start to illustrate the ways these different synchronization mechanisms can be used to implement each other. Here we're using a condition variable and a mutex to implement a recursive mutex. And of course, it also illustrates why a recursive mutex is somewhat more expensive than a non-recursive mutex, because there's extra work going on. There's an extra lock operation, there's the use potentially of the condition variable, and so on. So the bottom line here is that you need to think carefully about how to do synchronization. You need to learn what's available in your operating system. But most likely, you ought to try to find ways to encapsulate access to these low-level synchronizers by using higher-level patterns and frameworks, because that will be much more easy to program, much less error-prone, and in many cases, actually more efficient as well.